Hi, in this video, we're going to take a look at factoring trinomials yet again, but this time the a, in terms of the trinomial, the leading coefficient, is going to be bigger than 1. So in the previous examples, every time we factor the trinomial, it just had x squared at the beginning, and it's basically just 1x squared. And we were able to factor that using our factoring method, so let's just do a quick review of that. I want to take this trinomial and put it inside the area boxes. So I know that the x squared is going to go in the first box, the 12 goes in the last box, and somehow these two other boxes have to add up to 8x but make the entire area model puzzle work. So what we do is we try to figure out what are my factor pairs of 12 that are going to add up to that middle coefficient of 8. So we know that 1 times 12 is 12, 2 times 6 is 12, and 3 times 4 is 12. And the one that's going to add up to that 8, those like terms, is going to be the one that includes a 2 and a 6. So we start factoring on the outside. We've got our x times x is x squared. Now we know that 2 times 6 is equal to 12. And when we multiply together, just to do a quick double check, we've got 2 times x and 6 times x, which adds up to 8x. So we had our factors of x plus 6 on one side and x plus 2 on the other side to represent our two factors. Now we're going to do kind of the same thing, but we're going to take a look at when we have a number in front of the x squared term, which is why we call this factoring trinomials when that a is greater than 1. And you might notice that when we get our binomial factors, those leading terms in each binomial are going to multiply up to 2x squared. Okay, but it's somewhat of a puzzle. Everything else has to work too. So to kind of see how this works, what I'd like you to do is pause the video and just do a little practice problem. Multiply together 2x minus 5 times x plus 3 using the area model. All right, so just checking to see how you did here. You can follow along. I've marked my sides. I multiply to get what's inside the boxes, so 2x times x. Then I'm going to do 2x times 3. On the bottom row, I've got negative 5 times x. And then finally, I have negative 5 times 3. I see that I have like terms that can be combined. And my total is 2x squared. My like terms are going to add up to 1x. And then I have the minus 15 at the end. So this is how we multiplied polynomials together last unit. Now what we're going to do is basically work backwards. We're going to try to deconstruct this problem by starting with the area, the parts in red, and trying to figure out what those binomial factors are. So our lesson number 4, factoring trinomials, where ax squared plus bx plus c. The big question is how to get that middle term, the bx part, split into the two boxes. Because we know that when we factor the 2m squared, that's going to go in the first box. We know that the positive 20 is going to go in the last box. But what we don't know is how does that give us 13m when I add those two boxes together. So the first thing we want to do is set it up like I have here. I start with 2m squared go in the first box, positive 20 goes in the last box, and now we have to do a little we could do guess and check is certainly one method that will work. Think about, like, if I wanted to factor 2m squared, the only way I can really split that up, and you have to have an m in each one, is if I have 2m times 1m. Okay, or just 2m times m is 2m squared. Now there's lots of different ways that I could get 20 to get that, two numbers that multiply up to 20. It could be like 1 times 20, for example, or 2 times 10, or 4 times 5. So let's check and see which combination would actually give us, again, the key is this 13m when I add the like terms together. So the way I have it written right now is I would get 1m in one box and 40m in the other diagonal box. When I add together my like terms, I get 41m. That problem is I wanted to get 13m, not 41m. So I know that I have the wrong combination for the factors of 20. It's not 1 times 20. So instead, maybe we try 2 times 10. Okay, and we just check. Well, 2 times m is 2m. 10 times 2m is 20m. And I can already tell that that's not going to add up to 13. Or 13m. It's too big. So I go back. I try again. And you can keep doing this over and over again until you eventually find the right combination. Or there is another way that might be a little bit more efficient. Okay, so here's what you do. You multiply together the leading coefficient and the constant term. So if I multiply 2 times 20, I will get 40. And then I want to find my factor pairs of 40. 1 times 40, 2 times 20, 4 times 10, and 5 times 8. That's all my factor pairs of 40. Now, which of these has a sum equal to 13? In other words, which ones add up to 13? Looks like it's going to be the last ones, 5 and 8. Now, this actually means that I'm going to get, let's see, 5m in one box and 8m in the other box. And we kind of work backwards from here. So we think about, let me use my highlighter. Trying to think about how did we get, or how could we multiply to get 5m? It's when we multiply those two parts in green together. Move some of these out of there. There we go. So if we already had m on one side, then that means that this must be a 5 up there, since 5 times m would give me 5m. Now, if I try to figure out how to get the 8m, it's when I multiply those two things together. And I already have 2m on one side, so what times 2m would give me 8m? Well, I know that 4 times 2 is 8, so 4 times 2m is 8m. So when I check everything, check all my multiplications, make sure my area model fits. Okay, m times 2m is 2m squared, that works. 5 times m is 5m, that one works. Let's see, bottom left, 4 times 2m is 8m. And bottom right, 5 times 4 is 20. So I have the correct area when I add up all those parts, even these like terms. So I had 2m squared plus 13m plus 20 as my area. And now I can see that my factors are along the side and across the top. So I had m plus 4 on the side, because I had m and 4 more. That's one of my factors. And then I had 2m plus 5 across the top. So when I factor this expression, I'll get those two binomial factors. All right, now I know this is a lot, and that one problem is not enough to see the pattern and what's happening here. So I'm going to go through several more examples. All right, so here we have, we're factoring 3p squared minus 2p minus 5. So again, like I talked about before, I know that that 3p squared has to go inside this first box because of how we multiply them together in the warm-up. I know it's going to go there. I also know that the minus 5 is going to go in the last box. But what I don't know is how are these two boxes going to add up to negative 2p. That's the challenge. So we can start by trying to factor what we have. For example, I know that I have to multiply two things together and get 3p squared. So it must be 3p times 1p to get 3p squared. That's really the only way that we can break that down. Now to get negative 5, well, the only way to really get negative 5 is going to be like 1 times negative 5 or negative 1 times positive 5. So if I try, let's see, let's do 1 times negative 5 to get negative 5 in that last box. Now we have to check the rest of it. Okay, if I want to figure out what's in this box, I multiply 3p times 1, and I get positive 3p. If I want to know what goes in the last box, it looks like I'm multiplying negative 5 times p, and I get negative 5p. So let's check our area. Did we get the trinomial that we started with? 3p squared, check. Negative 5p plus 3p is negative 2p. That checks also. And then the minus 5 at the end. All right, so we actually have the right area right now. It all checks out. That actually worked out nicely on our first try. So then how do we write it as a factoring? Okay, so my total area is when I took 3p minus 5, make sure you group that together, and that was multiplied by the other length that had p plus 1 more, so p plus 1. So those are my two binomial factors that would give me a total area of 3p squared minus 2p minus 5. Now we got pretty lucky that our first combination worked. We didn't have to undo and try again. And sometimes you will. Sometimes it's a little bit more work. All right, so here we have our second example. 2n squared plus 3n minus 9. Again, I've got the 2n squared goes in the first box, the minus 9 goes in the last box, and we have to try to figure out how do these two boxes add up to 3n, positive 3n, and make everything else fit in our area model. We start by factoring the 2n squared. Well, what times what equals 2n squared? Well, I know it's going to be 2n times 1n is 2n squared. Now, in order to get the negative 9 at the end, there's a couple different combinations that we could use. 1 times 9, 3 times 3, but I have to include, it could be 1 times negative 9 also. And really with a negative 3 times 3, it's, if I flip the negative, it's still 3 times negative 3. So it looks like we've got three different combinations to check, and it could be where we have to flip the numbers too. So let's just start with, negative 1 and positive 9, like that. And let's check to see if it works out. Again, I'm looking for how do these two boxes add up to positive 3n. So my first box on the top right, I'm going to take 2n times negative 1. That gives me negative 2n. In the bottom left, I'm going to take 9 times n. It's like a multiplication table. Just do row times column. That's 9n. But when I add these together, I get 7n. That's not what I want. I want 3n. All right, so that's not it. It's not negative 1 on the top and positive 9 on the bottom. Undo that. Now, what's interesting is if I change these around and put the negative 1 on one side and the positive 9 on the other side, it's actually going to give us a different sum in the middle. So in the top box this time, I'm taking 2n times 9, which is 18n. And in the bottom box, I'm multiplying negative 1 times n, which is like negative 1n. And when I add those together, I'm going to get 17n. Okay, still not the correct combination. So let's go back and take those away. So it wasn't negative 1 and 9 in either order. Perhaps it's negative 3 and 3. Let's try that in that order. In the top row, I'm going to take 2n times negative 3, and I get negative 6n. In the bottom row, I'm going to multiply 3 times n, and I'm going to get 3n. When I add those together, I get negative 3n. Oh, that is so close. The only problem is we wanted it to be positive 3, not negative 3. Can you think about how I might get the same value but change the sign to a positive 3n? Wonder what would happen if I just flip those two numbers around. So instead of having negative 3 across the top, I'm going to put that down on the bottom. So the negative 3 down there and the positive 3 up there. Now when I multiply, I get 6n on the top, I get negative 3n in the bottom row, and when I add those together, it'll become a positive 3n, which is exactly what we needed. So for the factoring, down the side, one of my factors is 2n minus 3, and then my other factor is across the top, written as a binomial, n plus 3. Remember that because that 3 was positive, we use the plus sign in there. So for the factoring, my answers are those two binomial factors. So that time it took us a little bit of trial and error, but we were able to get there eventually. The more of these you do, the more you'll find little tricks and realize that certain combinations just aren't going to work. But that comes with practice. All right, for number 3, we have 3n squared minus 8n plus 4. We have the 3n squared in the first box. We have the plus 4 in the last box. We're trying to figure out how do those two boxes add up to negative 8n. All right, so let's start by factoring what we know. The 3n squared has to be 3n times 1n. That's the only way we can do that because 3 is a prime number. The 4, however, the 4 at the end, could really be broken down as 1 times 4 or 2 times 2 or negative 1 times negative 4 or negative 2 times negative 2. Now, if we really think about this problem and remind ourselves that these two like terms have to add up to a negative number, that kind of tells me it can't be two positive numbers. They have to be negative numbers. So it eliminates some of the options right away. I don't have to check everything. I know some of those just aren't going to work. So where do you want to start? Negative 1 with negative 4 or negative 2 and negative 2? I don't know. Let's try negative 2 and negative 2. Because at least then I don't have to flip them around and check the same numbers again. So think about what would I multiply to get that box, and what would I get? 3n times negative 2 is negative 6n. In the bottom row, I'd multiply negative 2 times n. I get negative 2n. Hey, look at that. When I add those together, I get negative 8n just like I wanted. Wow, I love it when it works out. So down the side, I have one of my binomials. It's 3n minus 2. And across the top, I have the other one. It's n minus 2. There is my factored form for number 3. All right, with our fourth example, again, the more you see, the better off you are. So I'm going to go through, I think, 5 total. We've got 5n squared plus 19n equals 12, or plus 12, excuse me. The 5n squared goes in the first box, and I can factor that right away. It's got to be 5n times n. It's the only way we can get 5n squared. To get the plus 12 in the last box, a couple different ways we can do that. 1 times 12, 2 times 6, 3 times 4. Or it could be negative 1 and negative 12, negative 2 and negative 6. But if we really look at, they have to add up to 19, positive 19n. It's not going to be negative numbers. So I only need to try the positive combinations. Now these factors over here are not going to add up to 19 because one of them gets multiplied by 5, and it kind of changes that number. So some of you might be able to look at these numbers and think, well, which one times 5 plus the other number times 1 would give you 19? That's a little bit harder. But you know what? I kind of see it right here. If I do 5 times 3, and if I do 1 times 4, and add those together, that's going to give me 15 plus 4, which is 19. That's exactly what I want to use. I want to use the 3 and the 4, and I have to make sure that the 3 is the number that gets multiplied by the 5 on the other side. So that's got to go here, because that's where I'm going to do 5n times 3 to give me that 15n in that box. Okay, so if the 3 goes on the top, the 4 goes down the side. Cool, I like it when it works that way. I don't have to check all of them. I kind of worked ahead. All right, so in this box, we said it's 5n times 3, 15n. In the bottom row, we do 4 times n, which is 4n. And there we go. They're going to add up to the 19n that we needed in the middle. So we have our factoring down the side. One of our factors is 5n plus 4. And then across the top, our other factors n. And remember, when it's positive, that means we use addition. N plus 3. All right, our final example, we have 6x squared plus x minus 12. And I realize I don't have this one color-coded, but that's okay. We don't need that anymore. We start with 6x squared in the first box, and the negative 12 goes in the last box. And we have to try to figure out, how do these other two boxes add up to 1x? That's the challenge. If we can figure it out, we've got our puzzle solved, and we can write it in factored form instead. All right, so 6x squared, the unique part of this problem is it could be 6x times 1x, or it might be 2x times 3x. We just are not quite sure. Also, that negative 12 could be any number of combinations where we have, 1 times negative 12, or negative 1 times positive 12, 2 times negative 6, or negative 2 times positive 6, 3 times negative 4, or negative 3 times positive 4. I think that's all of them. So that really gives us a lot of different combinations to try. There's actually a faster way of doing this. Instead of trying all those combinations, do what we did in the very first problem. If I multiply together the leading coefficient of 6 times the constant term of 12, or technically negative 12, I'm going to get negative 72. If I make a list of all my factor pairs of negative 72, and I find the ones that add up to 1, those are the numbers that I'm going to use inside the boxes. Okay, I know this is a little bit different than how we did the other ones, but there's so many combinations to check if we do it the other way. So let's see. Let's start this out. 1 times 72, 2 times 36, 3 times 24. You can check this on your calculator. You just do 72 divided by 1, 72 divided by 2, 72 divided by 3, and check to see what it divides out as. 72 divided by 4, I believe, is 18. 4 times 20 is 80, so that should be 4 times 18 is 72. Let's see, 5 doesn't work. 6 times 12, whoops. 7 does not work, and then 8 times 9 is 72. So there, those are our combinations of factor pairs of 72, but I need to make one number negative in each combination. So knowing that they have to add up to a positive 1x, my rules of adding a positive and a negative together tell me that the bigger number takes the sign of the sum. So my bigger number has to be the positive number, meaning the smaller number in each pair has to be the negative number. These all those little clues together really help us here, make our job a little bit easier. So which of these factor pairs are going to actually add up to 1x? Like those two boxes have to add up to 1. And this is the two numbers that are 1 apart. It's this one right there, negative 8 and 9. So when I put those numbers in our box, I can put them anywhere. I know that they're going to have an x attached to it because of how I've seen the other ones. So there, my 2 add up to 1x like I needed it to. And now we actually have to factor kind of backwards. This is probably the hardest part of doing it this way. We have to look at, in this area on the left-hand side here, what do these two have in common? Like a greatest common factor. What can I divide out of 6 and 9? And how, what can I divide out of the x squared and the x? Each of them has an x in it. The biggest number I can divide out of 6 and 9 would be 3, and they each have an x in it. And then if I do the same thing this way, what's the biggest number I can divide out of 6 and 8 would be, let's move that up, would be, I guess, 2, and they each have an x in it. So that kind of gets me started. So if I look at, now that I have, sorry, move things around here. There we go. Now that I have 3x times 2x is 6x squared, I can use that to kind of fill in the rest of the puzzle. Let me move my green piece over. All right, so that's going to help us figure out that blank yellow spot. What times 3x is 9x? Oh, well, I know 3 times 3 is 9, so that must be 3. 3 times 3x is 9x. All right, now if I move to the bottom row and figure out, well, what multiplies up to negative 8x? Something times something times 2x. This thing times 2x has to be negative 8x. Okay, so I know it's got to be negative. What times 2 equals 8? Well, that's got to be a 4. 4 times 2 is 8. So negative 4 times 2x is negative 8x. Okay, and then we just check our last box. It's really just a check step there, that 3 times negative 4 is negative 12. It works. Holy cow, that was a lot of work to get that last one. We still need to write our answer in factored form. We have 3x minus 4 as one factor, and we have 2x plus 3 as the other factor. Plus because we have the positive there. All right, so I know I showed you multiple ways of doing basically the same type of problem. Sometimes just guessing and checking and looking at factors of the first box and factors of the last box until it works out is enough. And other times there's so many different combinations, like on this one, that it might be easier to try what we did here. All right. So the only way that we really get better at this is we've got to just keep trying. So please look at that recommended homework. Try all of those. Make sure that you check your answers using the answer key. And then it's quiz time. All right. Have a great rest of your day. Thank you for watching.